So when we were looking at reasons why a limit might not exist, we mentioned the case of the limit being infinity. And so that's what we're going to address here, the infinite limits, or in other words, I put in quotes, limits of infinity. And it's a very important thing to talk about. We do have to remember that a limit of infinity is not an actual limit, but it gives us a lot of good information. So when we're talking about an infinite limit, what we really mean is a limit in which f of x increases or decreases without bound as x approaches a. So we're approaching some value, and the function values are either getting really big or really small. In other words, going to very large negative numbers, like negative 100, negative 1,000. And again, big note, when the limit is infinity, and that's why I have that in quotes, because it's not an actual limit. A limit has to be a number, a value. The limit does not exist. But by making this statement that limit as x approaches a of f of x equals infinity, that gives us information about how it doesn't exist. It tells us what the function is doing there. So even though we understand that the limit doesn't exist, we write infinity or negative infinity to describe it. All right, so let's look at some graphical examples here and see what we can make out of this. So we notice in this first example that as we approach a from each side, we see that the function goes off to positive infinity. Okay, so because what's happening there happens the same on both sides, now it's not an actual limit, each of the one-sided limits are doing the same thing in going off to positive infinity, I can write the statement down here that the limit as x approaches a of f of x equals infinity. Again, ultimate meaning, it does not exist, but that's how it does not exist. A little trickier in this second graph here, because we have slightly different behavior on each side. As we approach a from the left, we go off to positive infinity. But as we approach a from the right, we go off to negative infinity. And we have to be able to capture that in anything we say. So in this case, I would be restricted to saying the limit as x approaches a. I would have to say actually it does not exist. The limit as x approaches a from the left, remember, does go off to infinity or positive infinity, but the limit as x approaches, as x approaches a from the right is negative infinity. So in this case, I'm not able to characterize the limit with one statement, but I could characterize each of the one-sided limits. Okay, so interestingly enough, when I drew these graphs, I see something that's common to both of these graphs, and that's this dotted line that I've represented. So what graphical feature do we see? Well, that's the question. And here's what we get. If f of x approaches infinity or negative infinity as x approaches a, from the left or right or both, so at least one of the directions, then the line x equals a is a vertical asymptote of the graph of f. So you've likely seen vertical asymptotes before, but you didn't really formally know how they were defined. And this is how they're formally defined, by saying that you have a limit, at least on one side, going to infinity, and infinity, positive or negative. So let's look at a theorem here that kind of says this more formally. So in mathematics, we have a lot of theorems. These are provable statements. In this course, we're not going to prove the theorems, but we will take a look at the theorems in order to see what the language is like. So I'm not saying you need to be able to recite these theorems verbatim, but you should understand what they're saying, and that's how we have to break them down. Okay. So this theorem says, let f and g be continuous on an open interval containing a. If f of a is not 0 and g of a is 0, and there exists an open interval containing a such that g of a is not 0 for all x not equal to a in the interval, then the graph of the function h of x equals f of x over g of x has a vertical asymptote at x equals a. Okay, so let's break this down. So this makes a very formal statement about where we should be looking for asymptotes when we have some sort of fractional expression. Okay, the most common fractional expression we're going to look at are rational expressions, but this isn't limited to that. So I'm going to say here that the meaning is look for vertical asymptotes at places where the denominator is 0 and the numerator is not 0. Okay, we often get into a common sort of sloppiness of saying, oh, vertical asymptotes happen when the denominator is 0. And it's actually when the denominator is 0 and the numerator is not 0. That's why f of a not equal to 0, g of a equals to 0. And it's a singular place where the denominator is not equal to 0. And that's why the whole next part about an open interval where the denominator is not 0. That's getting very specific. This gives us one place to look for vertical asymptotes. Vertical asymptotes can happen for other reasons. They can be built into a function like ln of x. But when we're looking at fractional expressions, we want to be looking at places where the denominator is 0 and the numerator is not 0. So let's look at this example right here. Just this small example. We'll get to some more later. So if we have h of x is x minus 3 over x minus 5. Okay, so we have a fractional expression. It happens to be a rational expression, polynomial over polynomial. And so what we'd be doing is looking at the numerator and looking at the denominator. Let's start with the denominator. Obviously, the denominator equals 0 when x is 5. Now, the important thing about the numerator is the numerator is not equal to 0 when x equals 5. This is telling me that there is a vertical asymptote being the line x equals 5. Remember, the line x equals 5 is a vertical line. So, now you may say, oh, but what about 3? 3 makes the numerator 0. That's a whole different thing. Making the numerator 0 and not the denominator 0 just gives you a 0 of the function. Okay? To make that point clear, let me just give a quick little sketch of what this function looks like, the graph. What you'd be talking about is you'd be talking about a vertical asymptote here at 5. So this would be x equals 5 there. And then what the function actually looks like is you would have something like this coming down here, and you would actually have this coming down like this. All right. And, oops, sorry. And what we're saying is, yes, there's the vertical asymptote at x equals 5. Now, the fact that the numerator is 0 at 3 is actually just this fact right here. A very important fact in its own, but not what we're looking for in this whole idea of vertical asymptotes. So we're focused on the denominator being 0 when the numerator is not 0.